Pikachu! Pikachu! Ding, ding.
It's time for the moment you've been waiting for. Da 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 da. Da 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 da. Da 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 da. Da 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 da. Da 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 da. Da 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 da. Di da di di da di di da 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 da.
So now I'm going to talk about the blockchain. So the blockchain essentially has two files. One is the blockchain where a block is instantiated, and then the main is where the chain is actually created. So looking at the blockchain file, you'll see that it has a basic constructor, and this takes the previous hash of the block before it and then the new block's data. So here it just sets the values and it creates a new block in the chain, and it's all stored in an object array. And each time that a block is added, the data that is inputted has a specific hash unique to the characters that's in it. So this right here is creating the hash. And then we also just have getter functions, which are used in the constructor. And then if we look at the main file, we'll see that you first have to instantiate an initial block. And this is because if you try to delete or insert the first block based off actual data that you're intaking, the hash is subject to being changed, which can make it difficult to know where the head of the entire chain is. So in this case, the initial block will never be changed since it has no data, and that ensures that nothing is messed with the head of the chain. And then if you go down here, you'll see that the block is created, each block is created from an input text file, and in that file contains data from the Arduino serial output. So each line is read from the file, and that is inputted into the blockchain through this call. And this holding variable contains the hash of the previous block, which creates the link between the previous block and the current block. And the input data is basically just the file, the line from the file that is being read. And then here we're just printing out the data and the current hash and the previous hash of the block. And then we set the holding variable to the current block. So on the next iteration, it has the previous hash. And then if we go and we run the program, we will do this. And you'll see that a blockchain is created from an input text file. And if we scroll up, we'll see the initial block has no data, and it has this current hash just based on this line of code right here saying that there's no data. And then the previous hash will always be 0 since it's the first block. But when you go to the next block, this is the specific line that is pulled from the input text file. And then we have the current hash, which is unique to this input data, and then the previous hash, which is the same as the initial block. And if you keep going down, you'll notice that each previous hash points to the hash of the previous block. And I'll just show you the input text file just to show. It pulls each line by line. So this will be pulled from the serial output of the Arduino, and this is with each iteration, each time. So every 10 or 30 seconds, it'll pull this data from the Arduino sensors, and it'll put it into a text file, which is then put in the blockchain.
So this is our code. It's relatively simple, but it has 4 different systems integrated into one: temperature, piezo, power generation, and ultrasonic. And all of these have their own separate systems, but then they tie together with safety LEDs that go on when different conditions are met. And if you can see here in our serial port, you can read every instance the statistic of what it's taking in.
Somebody once told me the world is gonna roll.
The ultrasonic sensor alerts the user if their spinner is slowing down. Since the sensor has a peak triggered to echo frequency, as the spinner begins moving rapidly, the sensor cannot differentiate the distance between itself and the spinner. This causes the red light to flicker. However, once the spinner slows to a rate at which the sensor can accurately read distance, the red light will remain on, alerting the user that they are not generating power.
So specifically, this is probably the most creative part. It's a method to measure ultrasonic ticks based on the trigger pin and the echo pin. And this is just called later on in the void loop when you want to take like an easy measurement instead of having all this code every time. So the ultrasonic sensor sends out a click at a very high frequency on one end, and on the other end it waits until the click is returned to it based off of echolocation, and it'll time how quickly that happens, and based on that it'll give you a distance.
The piezo disc sensor alerts the user if their device is spinning at a rapid rate, in which power is successfully being generated. As the user spins the fidget spinner, the green LED will turn on, demonstrating that a satisfactory RPM is being reached. Otherwise, the LED will remain off, alerting the user that they are not generating enough power to charge their smart device. A specific threshold for changing the high or low voltage to the LED has been set, which is based on the weight and movement feedback of the fidget spinner on the piezo disc sensor. The temperature sensor is attached to the coil inductor. This will monitor the heat given off from the device as it is being spun. As the spinner is generating a current, the inductor gives off heat. It is important to monitor the average temperature given off by the coil because it will tell if the device is generating too much heat. This IoT data will allow us to further improve the product design by coming up with ways to cool the coil or even contain the heat, preventing potential safety hazards for the user.
So the way the circuit determines power generation is that across the inductor, when the power goes through, it's going to be read on an analog pin in the Arduino, and then that gets mapped accordingly. And it's a small range, but we're still able to notice it on the program, and we just print that out. It goes into our blockchain and we can verify it.
Here you can see a coil inductor generating voltage as it is lowered between the magnets. The magnets are on the outer bearings of the spinner and rotate around the inductor, generating a magnetic field. In order for electricity to be generated from the mechanical movement of the spinner, the field lines must be perpendicular with one another. As seen from the video, the peak voltage generated from the movement is around 4 millivolts. Unfortunately, this value is too low to power a phone. However, if an inductor with more coil turns and stronger magnets were used, a greater field and resulting electrical power would be generated, which would allow a smart device to be successfully charged.
I go hard in the paint.
Ready?
Yeah.
So you see how it's not in its ideal range? If I make it fast, it should pop into it. Blinking red light means it's working. Solid red light means it's stopped. It's version 1 of our spinner. As you can see, it's not charging right now. And it should take a second after I spin it for it to build up charge and work. Spin it faster. Oh, there it goes.
Oh, shoot.